Okay, so now we're looking at part 2 of chapter 9 on gravity. And so we're going to look at weight and weightlessness and gravitational fields in general a little bit. So the idea with weight, of course, is that force that you feel, but often it's the force you feel against your feet, okay, which is actually more the normal force when you're measuring your weight. And so weight is that force that you exert against the supporting force or the weighing scale. What if there's no supporting floor? Well, that actually is what we sort of call weightlessness. It's not that there's no gravity, it's just there's nothing that you're pushing against. So there's no support force. And so when you're in free fall, that is an example of weightlessness. You're definitely falling. You're falling because of gravity, but you don't feel any force against your feet. The other thing is that the force that you feel isn't always equal to the force of gravity, equal to your weight, where your weight is mg. So your normal weight is when your apparent weight, those are equal to each other. And so you stand on a scale and you've got a mass of, say, 12 kilograms. So your weight would be 120 newtons. Okay, that would be very small for an adult. Okay, so let's try that you are 50 kilograms, so your weight is 500 newtons, right? We've just been multiplying by g to get those numbers. So in that case, your normal weight is what is your apparent weight. That's what the scale is showing. So when does that occur? That your apparent weight that we would read on a scale equals mg. Well, that's going to occur, of course, when you have when you're not falling. Okay, so when your velocity is 0. And it also, though, can happen when you are moving, but you're moving at a constant speed. And those may sound familiar because those are the conditions for equilibrium. In that case, your weight downward, mg, is balanced by the normal force pushing upwards. Okay, so those two are in equilibrium, but that's not always what's happening in an elevator. When you start the elevator and let's say you're going up, you feel a force greater on your feet because you're having to be accelerated upwards. And so when you are accelerating upwards, then there's a greater force coming upwards than your weight downwards. So the apparent weight against your feet, you will feel that it is greater. And that it happens when you're accelerating upwards. So you've got an acceleration upwards, not just movement upwards. You can go at a constant speed and feel the same weight, but when you have an acceleration upwards. What about when you're accelerating downwards? Well, when we have a downward acceleration, basically what we're doing is we're allowing gravity to give us some acceleration, so we're not being supported as much. In that case, mg is going to be greater than the force against your feet. So you feel a little bit lighter when you're being accelerated downwards. So in that case, WA is smaller than mg. Now, when you're in an elevator ride and you go upwards, you accelerate first, Then you reach usually a constant speed, and then you come to a stop, and at that point you may feel a little bit lighter because basically you're decelerating, and so gravity is being allowed to bring you to a stop. So you may experience all of these things in one short elevator ride upwards. And when you start back down, then you get the downward acceleration first. You feel a little lighter, then you'll feel normal weight. And then when you come to a stop, you'll feel the acceleration upwards that's stopping you. Okay, so what about the last picture here? Well, here we've got free fall. The rope breaks, and by the way, of course, elevators can't really fall like this. But when you're in free fall, and this could just be you jumping off a step or a wall or something like that. Anytime you're just flying through the air, that's free fall. And if you're just obeying the forces of gravity. In that case, the scale is floating around with you, and so there's no upward force on your feet. And you are falling at the same rate as the elevator, as Galileo said. All these masses are falling with the same acceleration, and that's what we call zero weight. In other words, there's zero apparent weight. But you still have the force of gravity on you pulling downward. It's just as pulling everything at the same accelerated rate. So everything is falling at 10 meters per second squared, or of course, 9.8 is the real number, right? Okay, so everything has an acceleration equal to 10 meters per second squared. All right. Now, this is what happens out in space, too. What we call free fall is just when the astronauts give in to gravity. So we'll look at that a little more later. Meanwhile, here's what we were just writing. So the apparent weight may or may not be equal to the mg, right? But the apparent weight is your support force, and that's normally what that force that we feel, that we think of as weight. Yes, so acceleration is 0, then the apparent weight equals mg. If the acceleration is up, then the apparent weight is greater. If it's down, the apparent weight is less. If acceleration equals g, then you are in weightless conditions, which again does not mean that you don't have a gravitational force. It just means that you are giving in to that gravitational force and you don't feel a support force. So when you fall off a cliff, okay, or if you're out in space, does the astronaut not have any gravitational force on him? Well, he actually has plenty of gravitational force. And that actually is what keeps the astronaut in orbit around the planet Earth. So the space shuttle, the International Space Station, people are floating around in the International Space Station. Does that mean that it's not responding to gravity? It is. It is trying to fall towards the Earth. But because it has forward motion, it just keeps going in a circle. And we'll talk about that in another chapter. Anyway, so this is the idea of weightlessness. The body responds as if the gravitational forces were absent, but they really actually are there, but they are not supported. And so that's one of the problems with astronauts in space, is they have no forces to push against, which, remember, we talked about how they have bone loss up to 2% per month because they're not using their bones to support themselves. So yes, the astronauts in the space station they're all orbiting together. So the individual people in here are in the same orbit as the space station. And so they all move together, they're all falling together. So you don't notice that around you. You are freely falling at the same rate as the station. So just like the elevator would be falling, and you would keep, you would be floating around in the elevator. Okay, now gravity is also called a gravitational field. The idea that it exists, even, if there's nothing else there, the idea that it still pulls on things. Okay, so when you're in a gravitational field, you feel the force of the gravity against you. So what would happen if you were able to get to the center of the Earth? Is there a gravitational field there? Well, let's examine that a little bit. Let's drill a hole through the center of the Earth, drop a ball down. What's going to happen to that ball? And what happens is that the gravitational force still exists for most of the trip, but it depends on the mass of the Earth that's below where you are. So normally this would be like if you were saying, okay, the mass of a person here and the mass of the Earth. The mass of the Earth at the surface includes all the Earth's mass. But as you go deeper down, what happens is you are actually acting like you're on a smaller planet. So if you are this far down in the hole, it's as if the gravitational force is only due to some small planet underneath you. And the closer you go to the center, the smaller that planet is. Till finally you're at the center, and then the gravitational force would be zero right at the center. So as you would fall, what would happen is that the acceleration would get less and less, but you would start out falling with an acceleration due to g that would be equal to g, so 10 meters per second squared. When you are halfway down, the acceleration would actually be half as much. When you get to the middle, it would be zero. But does that mean you would stop? No, because you've got all this momentum, right? So it's kind of like a pendulum swinging. Very similar. You start out with lots of potential energy, and then you go right through the center. You're going very fast with velocity, okay? Even though there's no acceleration, that doesn't mean you're going to stop. It just means you're not accelerating. And then as you pass through it, well, now the acceleration is the opposite direction. So you start to slow down. And then you get to the surface, and now the acceleration is exactly in the opposite direction. And what happens? Well, you could just touch the surface and then go whoosh, back down the other way again. So it would be like a pendulum that you would go back and forth, except through the core of the Earth, bouncing back and forth. If you were able to stop right in the center, then yeah, you wouldn't feel a force in any direction. So this is actually a graph showing the gravitational field inside the planet. So this part is for inside the planet, and this is out past the surface, so the radius of the planet here. And so you can see how amazingly the math works out to be a straight line inside the planet, which is why when you're halfway along, your gravitational force is half as much. Okay, but when you're outside the planet, it's that inverse square law. So when you're at a radius of 2r, the force is 1/4 as much. Anyway, so that's just the way the math works out. And there's a little bit of discussion on that. But let's talk about this. What is the force of gravity on an astronaut who is in orbit? So this is one of the homework problems you're supposed to think about. And so where is the space shuttle? Or the International Space Station? Is it at 2r? Is it at 3r? Where is it? Well, it turns out that the International Space Station and the Space Shuttle were usually only flying about 200 kilometers above the surface of the Earth, which is 6,000 kilometers. So the thing is that they still had a very strong gravitational force on them because they were very close still to being to the Earth. And so it's not that the astronauts have no gravitational force. In fact, they have a lot. It's not zero. In fact, it's closer to 94%, I think. You guys are supposed to do the math on that. that they still have almost all their gravitational force. And that's good, because if they didn't have a gravitational force, they would just take off straight and leave orbit. But as it is, gravity pulls on them and acts as a centripetal force that keeps them moving in a circular orbit. Okay, so that's the end of that section. And we're going to go on to the next part 3, about tides. Okay, I'm going to stop and start.